Soummya Data, and this is Built to Trust. Today we are going interface first. Contracts, seams, and integration without drama. If you build hardware, software, controls, or robotics, most of your real risk does not live inside the boxes. It lives where boxes meet. Timing, units, error handling, version, drift, safety interlocks. The seams decide whether programs slip or ship. The good news is simple. When you make seams the product and you treat interface truth as a first-class artifact, integration becomes boring in the best way. Today I will show you how to do that. Here is the path for the episode. First, what a seam is and why it hides risk. Second, how to write an interface contract you cannot misread. Third, how to build contract tests that run every day and prove the boundary works. Fourth, seam soaks that run long with jitter, loss, and reorder so reality cannot surprise you. Fifth, versioning and freeze windows with interface change notes that keep everyone honest. Sixth, evidence at the boundary. Seventh, a fault menu your teams will actually run. Eighth, how to organize around seams with owners, a public seam board, and a weekly cadence. Ninth, the small set of numbers that tell you if the seams are healthy. 10th, stories where this approach turned chaos into calm. Then we will land with an action kit you can copy on Monday. Let's start with the seam. A seam is the boundary between two parts of a system. In software, it can be an API with a payload, a queue with ordering rules, a file with a schema, or a driver with timing guarantees. In hardware, it can be a connector with pins, voltages, and a critical dimension that must hold during vibration. In controls and robotics, it can be a bus with jitter budgets, a pose estimate contract, a watchdog handshake, or an interlock between motion and power. In operations, it can be a station handoff with a torque value and a photo that must exist before the next step. Seams are where assumptions meet physics. They are where should crashes into did. That is why teams feel confident inside their boxes and anxious during integration. The cure is to bring the truth of the seam into the light and to make it easy to prove. How do you write an interface contract you cannot misread? Use short, measurable fields. Give every value a name, a unit, a range, and a meaning. Define how you handle errors, define timing budgets, define ordering rules, define idempotency, define versioning, define safety interlocks and the conditions that must be true before an action is allowed. Stop writing prose nobody reads. Write tables and examples people can run. Here is a pattern that works. Start with a purpose line in one sentence. This interface carries pose updates from vision to control at 50 Hz with a jitter budget of 5 milliseconds, and it must allow a safe stop on stale data. Then define the message fields in a small table. Pose X in meters, range -10 to +10. Pose Y, same range. Pose Z, same quaternion W, X, Y, Z, unitless, normalization tolerance, velocity vector in meters per second, timestamp in microseconds since epoch, producer ID, consumer ID, then define the rules. Messages must arrive in timestamp order. If two messages share a timestamp, drop the second. If the gap between timestamps exceeds 60 milliseconds, the consumer must enter a degrade mode and publish a safe stop request. Define timing budgets. Producer to consumer end to end must be under 20 milliseconds P95 and under 40 milliseconds P99. Define how you handle errors. If a field is missing, set an explicit error code and drop the update. Do not guess. Define idempotency. Replaying a message with the same timestamp must produce the same state. Define versioning. Include a schema version field. If versions differ, the consumer must run the compatibility path you declare or reject the message and raise a change note. For physical seams, do the same. Define the connector, pin numbers, voltages, tolerances, pull-ups, pull-downs, length limits, strain relief, the torque spec for the shell, the order of insertion, the environmental limits for vibration and temperature, the safety interlock conditions that must hold before power can flow. Write this like a checklist an operator can use. Once you have a contract, you need proof. Contract tests are the proof you run every day to show the seam behaves. They are small programs or fixtures that send and receive real messages through the real boundary and check that the results match the contract. A good contract test is tiny, fast, and loud when the contract breaks. It runs in your build. It runs in your lab. It runs on the bench. It uses the same IDs and the same logs as the rest of your system, so you can compare real runs. A contract test includes happy path examples, boundary values, and negative cases. It checks units and ranges. It checks timing. It checks ordering. It checks idempotency. It checks error codes. It checks that safety interlocks fire when they should and stay quiet when they should. If your interface is physical, your contract test may be a small board with a known good pull-up and a scope script that checks rise time and ringing. It might be a shaker profile to confirm a connector stays latched. It might be a torque witness on a CT cough fastener with a gauge that logs value and timestamp. Make contract tests easy to discover and easy to run. Put them in a folder called seam tests at the root of your code or hardware repo. Give each test a name that includes the seam name. Seam underscore pose underscore V2 underscore contract. Seam underscore power 24 volts underscore rev B underscore CTQ. Seam underscore bus underscore can underscore V1 underscore jitter. When someone changes a seam, they run the test and they post a link to the run in the change note. The run should include a screenshot or a log snippet with IDs so you can see it passed. If a test fails, treat it like a unit test that broke at the center of your architecture. Stop and fix the seam before you keep going. Contract tests prove the shape of the seam. Seam soaks prove the seam under time. A seam soak is a long-running test with realistic stress. For software and controls, this means you run with jitter, packet loss, reordering, and duplication. You set a profile that looks like your field. You log P95 and P99 on latency and on jitter. You track error rates. You set stop-loss triggers. If the error rate exceeds a threshold for a set window, you stop, collect evidence, and fix. For hardware, a seam soak may be a temperature cycle or a vibration dwell paired with a power cycle pattern. You log voltage droop. You log connector micro-opens if you have them. You check that interlocks hold. For a station handoff, a seam soak can be a sequence of units tacked with the same operator swap pattern you expect in production. The point is to make the seam boring under the stress you expect in the field. How long should a seam soak run? Use your 6-week cadence. In the first week after a change, aim for a 12-hour soak with 2 stress profiles. By the end of the second week, run a 24-hour soak with the worst expected profile. Before a demo or flight or ramp, run the soak again under a freeze window and post the evidence in the go or no-go. The soak is not a ritual. It is a way to see what reality does to your neat plan. When you write the soak, include the pass gate in one sentence. Done when P99 latency stays under 40 milliseconds for 24 hours with 0 critical alerts and fewer than 1 in 10,000 dropped messages, measured in the health panels observed in the ops dashboard. Logs linked here. When the pass gate is green, people breathe and ship. Now versioning and freeze Windows. Interfaces drift because people optimize and people forget. Drift is natural. Breakage is a choice. You prevent breakage with 2 small tools. Version fields inside your messages and change notes for interface deltas. Add a schema version field and bump it when you add or remove a field. Keep backward compatibility for 1 version window if you can. When you cannot, declare a freeze window, land the change on both sides of the seam, and test it together in a branch environment with contract tests in a short soak. Write an interface change note every time the seam changes. put a title that includes the seam name and the version change. Seam underscore pose V1 to V2. Include what changed, why, the compatibility plan, the tests you ran, and a link to the evidence. Tag the owners on both sides. If a seam change can impact safety, include a short safety line that says whether any hazards are affected, which controls proof safety still holds, and which evidence you refreshed. This is management of change for seams done small. Freeze windows protect you during landings. Declare a short window where seam versions cannot change. 36 hours is a good default for a weekly landing. If a critical fix must go in, write a change note with the reason and the rollback plan, and run the contract tests in a fast soak. The person who approves the change writes a single sentence that says why this exception is worth it. The key is not to prevent all change. The key is to make change visible and reversible. Evidence at the boundary is what makes audits painless and incidents short. Every seam should have an evidence pack that includes a screenshot or log snippet from the last contract test run, a screenshot from the last soak showing the key panels, a small table with pass and fail counts for the last week, and a link to the current interface control document with a diff to the previous version. For physical seams, include a photo of the connector, the torque value for the shell, the CTQ measurement with a timestamp, and the shaker or temperature profile used. Store these packs where your teams already look for evidence. Link them from the seam board and from the interface runbook header. If someone asks, "Are we safe to fly this seam?" you should be able to click once and show the last green run. A fault menu is what keeps seams honest during the week. Make a short list of faults you inject regularly. For a bus interface, flap the bus with a pattern that drops every net packet, reorders chunks with a small probability, duplicates a message occasionally, and skews the clock by a tight distribution that matches your hardware. For a sensor, drop out for a short time, add noise, hold a stale value, or drift a bias. For power, brown out for a set duration under load, spike then return. For mechanical seams, add vibration at a frequency and amplitude that matches your environment, and measure micro opens if you can. For a station handoff, remove the expected photo, send a bad torque value, or present a part with a borderline CTQ. The point is to choose faults people will actually run. Keep the list small. Tie each fault to a pass or fail rule and to a runbook step with a screenshot to capture. Over time, you can add faults as you learn. The best fault menu is the one your team uses weekly. Organize around seams so responsibility is clear. Name seam owners, one name per seam and a backup. Publish the list in a visible place with a short description of each seam and a link to the interface contract, the contract tests, the seam soak, the evidence pack, and the runbook. Create a seam board and review it weekly for 15 minutes. The seam board lists each seam, the current version, the last contract test, run date, the last soak date, the last failure count, and any open change notes. Red flags appear only when a decision is needed. If a seam is about to change and you need to pick a date, it is red. If a seam is failing and you need to pick an option, it is red. If everything is green, you do not talk about it. The seam board is not a status theater. It is a way to land decisions fast and to keep attention on what matters. Here is a simple weekly flow. On Monday morning, each seam owner runs the contract tests or posts the link from the continuous build that shows they ran within the last day. If anything failed, they file a bug and tag the partner. On Tuesday, run a short seam soak for any seam that changed last week and post the panel screenshot. On Wednesday, hold a 15-minute seam board review. Talk only about seams with decisions. On Thursday, hold freeze windows and run seam soaks for any seam on the path to a landing. On Friday, include seam numbers in the truth rollup. Contract test pass rate, seam incident count, any interface change notes opened or closed. The key is not meetings. The key is to make the boundary a first-class citizen of your weekly cadence. What numbers tell you whether seams are healthy? Keep it short. Contract test pass rate by seam daily. Seam incident count and severity for the week. Change fail rate at interfaces. Mean time to recover at a seam. Percent of seams with a soak in the last 14 days. For production, percent of station handoffs with complete evidence photos and torque values. For safety, percent of seams with current run book headers and last dry run dates within policy. Put these numbers on a small panel. If a number moves the wrong way, ask why and pick a fix. If a number stays green, move on. Stories make this real. A controls and perception team had a pose seam that looked fine in the lab and flaky in the field. The contract said 50 hertz. The real bus delivered bursts and gaps. The soak ran with a simple average delay. Reality had jitter spikes. We wrote a new contract with timing budgets and a degrade rule on stale data. We wrote a contract test that checked order and impotency. We wrote a soak that injected jitter and loss. We added a watchdog and a safe stop request on a stale stream. Field incidents dropped to near zero. The seam got boring. The team went back to improving quality instead of fighting ghosts. A hardware group had a connector that latched in the bench but opened under vibration at a certain frequency. The contract did not say anything about strain relief or torque. The seam ran long only during demos when wire routing was tight. We added a mechanical CTQ for strain relief, a torque value for the shell, and a photo step. We added a shaker dwell to the seam soak. We printed the runbook header and taped it to the bench with a QR code to the live dock. The latch problem never came back. First pass yield improved because the station step caught variation earlier. A platform team had an API seam to a partner that changed often. The partner posted changes in a dock nobody watched. Outages happened during important demos. We added a schema version field, a weekly seam board with the partner's version noted, and a rule that any seam change gets a change note with a link to a contract test run. We added a seam freeze window before demos, and we tested in a branch with a short soak. The surprises stopped. The partner enjoyed the clarity too because they could plan big changes in a window and see the proof. Let's land on an action kit you can copy. First, write one interface contract this week for a seam that matters. 1 page. Start with the purpose in 1 sentence. Then a field table with names, units, ranges, and meanings. Then the rules for timing, ordering, error handling, idempotency, and versioning. For physical seams, list pins, voltages, tolerances, torque, insertion order, and environmental limits. End with the safety conditions that must hold before an action is allowed. Put the dock where people work. Link it from the seam board. Second, create a tiny contract test. Make it fast and loud. Happy path. Boundary values, negative cases, ordering check, idempotency check, timing check, error code check. For hardware, write a bench script that measures rise time and ringing and saves a scope screenshot with a timestamp. For robotics, write a short loop that feeds pose messages with ordered and out of order timestamps and checks the consumer behavior. Put the test in a folder called seam tests and put the seam name in the file. Wire the test to run in your build and in your lab. Third, write a seam soak for the same boundary. For software and controls, write a script that pushes messages with jitter and loss and records P95 and P99 for latency and jitter. Add a stop loss trigger and stop if it fires. For hardware, write a soak that cycles temperature and shakes at a known bad frequency, then power cycles under load and records droop and noise. For a station handoff, write a soak that runs a pattern of units at TOCT with the expected operator swap and records photo and torque evidence rates. Make the soak predictable and repeatable. Put the pass gate in 1 sentence at the top. Fourth, add a schema version field if you do not have one. Write a short rule that says how you bump the version and how long you promise compatibility. Write a short interface change note template. Title with the seam name and the version change. Fields for what changed, why, the compatibility plan, the tests you ran, and the evidence links. Add a small safety line if the seam has a hazard impact. Fifth, create a seam board, a table with one line per seam, columns for owner, backup, version, last contract test date, last soak date, open change notes, and a small red flag if a decision is needed. Review it for 15 minutes on Wednesday. If nothing needs a decision, end the meeting in 5. The board is not for speeches. It is for decisions. Sixth, pick a fault menu. 5 items. For a bus, drop, reorder, duplicate, jitter, and clock skew. For a sensor, dropout, noise, stale value, and bias drift. For power, brownout, and spike. For mechanical, vibration, dwell, and thermal cycle. For a station handoff, missing photo and wrong torque. Tie each fault to a pass or fail and to a runbook step with a screenshot. Run 1 or 2 faults per week at a seam you touched. 7th, write an interface runbook header. Name and purpose, owner and backup, last updated and last dry run. Prereqs, escalation ladder, rollback summary, pass and fail gates. Then write steps, action, expected result, evidence, guard, timer, rollback. Rehearse at 3 in the afternoon so it works at 3 in the morning. Print the header and tape it where hands go. Put a QR code to the live doc. 8th, put seam numbers on your status panel. Contract test pass rate, seam incident count, change fail rate at interfaces, mean time to recover, and percent of seams with a soak in the last 14 days. Keep it tiny. Use it to focus attention. If a number is red, pick one fix. If the numbers are green, go build. 9th, tie seams to growth. Give people reps that say own a seam for a cycle. Write a contract test for this seam. Run a seam soak and land a go or no-go. Add seam ownership as a line in your ladder. Level 3 to 4 is own a component seam and write the run book others use. Level 4 to 5 is shape a system seam and design a freeze window others respect. This grows people and hardens your system. 10th, connect seams to safety without paper cuts. For each hazard that touches a seam, write the control that lives at the seam and the evidence that proves it. Put the hazard, control, and evidence on one line. If you change the seam, update the line. If you run a seam soak, drop the screenshot in the evidence link. Safety becomes a living story, not a binder. Let me close with a short view of how this ties back to our season. In episode 7, we made change safe and visible with management of change. Interface change notes are that habit at the boundary. In episode 8, we designed soaks that tell the truth. Seam soaks are the precise place where time meets the boundary. In episode 10, we built calm status with one number and one risk trend. Seam pass rate is a perfect one number. Seam incident rate is a clean risk trend. In episode 11, we wrote runbooks that actually run. Interface runbooks let you recover when the boundary wobbles. In episode 12, we grew people with reps. Seam ownership is one of the best reps you can give. Interfaces will always change. Partners will always optimize. Networks will always jitter. Reality will always test you. When you put your attention on the seams, write contracts people can run, and keep proof cheap. You take control of the part that used to control you. Integration stops feeling like a cliff and starts feeling like a series of small landings you know how to make. That is what shipping feels like. Calm, boring, on time. If this helped, follow Built to Trust wherever you listen. Hit subscribe. Share it with a teammate who has ever stared at a log and wondered why 2 boxes disagree. Your ratings and reviews help more builders find the show and build with more truth and less drama. Next up, we will talk about supplier reality and production readiness, how to qualify, how to survive shortages, and how to keep quality high during ramp without turning your week into paperwork. I'm Soummya Data. Thanks for listening.